Moakler, postdoc funded by the Muri grant, will speak about the project concerned with quantification of rare transitions in arrays of nonlinear oscillators with small periodic forcing and small noise. The approach is based on approximating the arrays of nonlinear oscillators with so-called analog Markov chains. So please, Christopher.
Thank you. So I'll be talking about maybe a little more succinctly approximating noisy nonlinear oscillators using Markov chains. So the kind of really the mathematical basis of this is the Duffing equation to model oscillators with dampening. And in our case, we're also adding this noise term. So we've got the Duffing equation with this added noise term and the periodic forcing term here. Here I've got an example of an experimental system done by Salenti, who just graduated from Maryland, where he's got the system of an oscillator, and it's got this periodic forcing term. And you can see here, it started off in this very large amplitude regime. It'll loop over in just one moment. It starts off in this large amplitude regime, going kind of wild back and forth. But then after a little bit of time here, it'll transition into this much lower amplitude regime here, which you can see. So these transitions between these sorts of attractors, the high amplitude attractor and the low amplitude attractor, are what we're interested in this work. Some more motivating examples besides just this experimental system. You can imagine the fins on one of these turbines for a jet plane, for example, or other kinds of turbines. The fins themselves, they can act as nonlinear oscillators with a periodic forcing there. They're rotating at this typically a constant speed, but then the actual fins themselves can oscillate, up and down perpendicular to this rotational plane here. We don't typically see the nonlinear effects as much in these very large fins, but for some of these smaller systems like these vibrational energy harvesters that you sometimes see discussed being deployed underwater to harvest the energy of ocean currents and ocean waves and things like that. These are much smaller fins, and things like this are much more subject to those nonlinear terms, which makes the dynamics much more complicated, much more interesting, much more rich. Some of the previous work that's been done on this, Salenti, that graduate student, Professor Cameron and Balachandran, also at Maryland, was looking at determining these most probable escape paths in these across these quasi-potential barriers, which describe these sorts of systems. They were looking at this approach for single oscillators, as well as a couple of coupled oscillators, 2, 3, and 5 coupled oscillators. The technique that they performed in this work here, one shortcoming of it was that it wasn't able to determine the escape rate of the frequency at which you will go from one attractor to another attractor. They weren't able to determine that escape rate, and they also were not able to extend it to noise that isn't of the white variety. When you have these oscillators coupled in this manner with this coupled at this base here, the noise that you might expect here is not actually going to be white noise. It'll be some other version of noise. And those ones are perhaps more interesting because of these motivating examples here where, for example, they aren't white noise driven. The approach that I'm going to talk about today, is based on this idea of transition path theory, and more specifically, discrete transition path theory. We're looking at modeling these systems as Markov jump processes, and there was a theory for transition path, formulation of transition path theory for these Markov jump processes that was outlined in 2009 by these folks. And instead of treating this space as a kind of continuous space, which transition path theory did previously, we instead start to discretize that space. And when we discretize that space, a lot of those continuous formulations, they have to become discrete. So for example, the forward committer, this Q plus the the probability that you're going to go from region A into region B without returning back to A. You can think of that as a transition, in this case, from a tractor to a tractor. The probability that you do that is given by this forward committer function, and we can actually solve that by solving this system of equations, which I'll get to a little bit more in a bit. Here, A and B are those sets of interest. So we can think of that as the high energy, the high amplitude attractor and the low amplitude attractor from that previous version. The backward committer is a kind of opposite, going from B to A without returning back to B, defined in this similar fashion. We also need a couple of these other terms, the invariant distribution, which is the distribution pi, such that this P here is the transition probability of going from one state to another. We return back to pi. We can get these other things, probability distribution of these reactive trajectories, calculate also using that forward and backward committers. The probability current, how likely we are to be in one of these reactive trajectories, the probability that the reactive trajectory goes through one of these states is given by this. And now we can start calculating things like the transition rate of going from A to B using this probability current. And finally, we can calculate this escape rate. The escape rate is proportional to this transition rate. We can actually get this exact equation here. And that was one of the shortcomings of that previous approach. But using this discrete transition path theory, we can start to calculate these sorts of things. So what I've done here is I've applied it to one nonlinear oscillator, just a single nonlinear oscillator like you saw in that video. And in particular, I've got one described by this equation, this nonlinear equation with these sets of parameters, and then this degree of noise here. This system has two attractors, one that's high amplitude, one that's low amplitude oscillations. And what's interesting about this system is that the basins around these attractors are about the same size. So now how do I actually study this thing? How do I actually form this Markov probability matrix? Well, first I need to discretize the space. So to discretize the space, I form a point cloud in this space. So this point cloud I generate by simulating very long trajectories from either one of the attractors, the low amplitude or the high amplitude attractor. And I simulate very long trajectories at an increased level of noise. And that's important. So this is the level of noise for the actual system that might describe an experimental system. To generate this point cloud, I run that simulation at a much higher level of noise so I can more thoroughly sample the space. These long trajectories, I say long, I mean something along the lines of maybe 5,000 periods. So here, the period is given here. Run it for 5,000 of those periods from either one of these attractors. I then see where each of those trajectories was at every period, and I collect all of those together, and I form this point cloud, which samples this state space. From that, I now need to understand how the system will transition between, point 1 to point 2 to point 3 to all these different points. And to do that, what I do here, I've got a little cartoon diagram of it. We take this red point here, let's call it point 1 for now. From point 1, I simulate a bunch of trajectories for a single period of the oscillation. And what I get out of that, it might be, for example, all of these different blue points. So after one period of that oscillation, I ended up at these blue points on this point cloud. And from that, I can actually learn the distribution, the probability that going from point 1 to any of these other points may occur. So I'm basically fitting a Gaussian distribution here. I'm learning the parameters of that Gaussian distribution. And now I can calculate the transition probability going from point 1 to any of these other points that it maybe didn't necessarily fall along. I have to end up cutting off that Gaussian distribution after 3 sigma, just because it's probably not going to go to those. I don't need to worry about those transitions. And when I do that, I can form the transition probability matrix. From that transition probability matrix, I can form the generator of the of the dynamics. And with that, I can start calculating things like the committer function, like I showed you that equation before. I solve a system of equations related to that generator, that L, that little L in my equations before, and I get things that look like this. So here I've got the committer function. If we start here, we're much more likely to end up over here. We're unlikely, not as likely to go from over here into this position over here. And we're actually really able to determine this area where we've got about a 50% likelihood. This is often very difficult to determine, but with this process of generating this point cloud, we're actually able to determine this pretty well. Over here, I've got the saddle points and then these two attractors. Like I said before, I can also calculate things like the probability density of reactive trajectory. So how likely am I to end up at one of these points along these reactive trajectories? You can see the saddle point over here is a hot place to be. You can do things like the total effective current. And then again, from this information, you can start to calculate that escape rate. So that was a kind of a toy model, maybe not a toy model, but a simpler model. And now I wanted to also apply it to something that we actually had experimental results for. So over here, I've got the system. I believe this is the system from that previous video where I was at, Salenti in his thesis work was actually able to learn these parameters to describe the system. And over here, yep, got the video. Again, this system generates basins that look like this. So you can see here, we've got one rather thin basin and then one much larger, thicker basin. This blue is a kind of a numerical artifact. If you end up over here, numerically, you explode out to infinity. Luckily, this thing doesn't explode out to infinity in the real world, though. So I wanted to try to run that same procedure on this new model, this new system rather. And when I did that same procedure of generating the point cloud of running these very long trajectories, I ran into a bit of an issue. I did the same thing where I ran 5,000 periods at each of these attractors. But this attractor, it was very easy for it to escape out into this attractor and then just hang out here for a very long time. And you see, I don't really sample this region of the state space very well, this kind of transition area that I'm very interested in. So I need a way to overcome that, because again, I'm very interested in that transition region. A lot of the interesting dynamics occurs in that region. I need to well sample that if I want to form those stochastic transition matrix. So I need to improve my point cloud somehow. And here I've got the results of that improvement. Here I'm showing those basin boundaries and the two attractors. And you see here, I'm much better at sampling this space now, even this transition space. So how do I do this? Well, actually, I just went in and sort of manually added in these points where each of those transition points from over here, I just add a little bubble of points, just a little small point cloud at each of those individual points to kind of beef up the sample points that I can work with. I think that this can be extended more generally. If you see transition points in a point cloud that you generate, they aren't well sampled, there aren't very many points around them, you can just slap on one of these clouds and improve that discretization of the space. When I do that, I get some pretty nice looking committer functions. Here you can see this basin boundary over here is pretty well sampled. And over here, I'm getting the probability density. There's a little bit of an offset here where this looks like the hot place to be, but the saddle point is slightly offset. I'm not sure what's causing that just now. But where do we go from here? I've applied this thing to an experimental system and I'm getting some pretty good results. Where do I go from here? From here, I start looking at things like coupled oscillators, right? This was just an example of a single oscillator. I would be interested in applying this to, n coupled oscillators. So to do that, I get a, much more complicated equation. The space becomes more complicated. It's much more higher dimensional. So I'm going to need to be able to sample that higher dimensional space well. And I believe that this, running the simulation at a higher level of noise to sample the space, then potentially going back in and adding additional points, we'll be able to effectively sample this higher dimensional space. Again, this increasing the number of coupled oscillators, we might get more basins, we get a higher dimensionality. So getting a good grip of that state space with those point clouds is going to be very, very important. But this approach should work quite well for that. And some other future directions of this would be to more thoroughly match this with the experimental data, do a more thorough comparison, and then also extending this to different colored noises, because like I was saying before, a lot of these experimental systems, they aren't white noise driven, they're driven by different sorts of noise. I think I'm done.
Thank you.
Thank you.
Stop sharing.